Everyone, my name is Geronimo. Before we start, I'm just curious, how many of you are cloud operators or are interested in? Okay. And what platforms are you on? Okay. Dan?
AWS.
Okay, cool.
DigitalOcean.
Excellent. Awesome. So my name is Geronimo. I'm going to be discussing software-defined storage and Asterisk today. This was, as a cloud operator, one of the bigger challenges we've had to overcome, as the amount of data we have to store, process, back up, and replicate adds up. It's definitely one of the greater infrastructural challenges we deal with on a daily basis, so it's what we're going to be discussing today. My company name is Nexicom. We are Unified Communications as a Service company, headquartered out of New York, with offices in Buenos Aires and Dallas. And we primarily focus on Unified Communications as a Service and call center as a service, but also do a lot of custom applications for customers in the cloud. So just to bring a little context to the conversation, I'm going to start talking about, I guess, the big three pillars of cloud computing. I'm sure this is familiar to everyone, just in case. Typically, when discussing cloud computing solutions, the three pillar elements we talk about are networking nodes, compute nodes, and storage nodes. And those are the three integral modules of cloud computing that allow us to segregate different functions across our data center networks in order to deploy it as efficiently as possible. And the assumptions in this talk, right, are that although there is bare metal cloud computing out there, the assumption is, for the purposes of this talk, that we're talking about KVM and Xen server virtualization. We're assuming 10 gigabit networking, and we are assuming libVRT and libRBD deployments in all KVM scenarios. So just as a quick review, the storage appliance model is what we all grew up on, right? Storage networks that were expensive, extremely proprietary, and are really, I mean, the biggest tech acquisition in history, I think, was Dell's acquisition of EMC this week. Proprietary hardware and software, living inside proprietary vendor equipment with a proprietary commitment, a support commitment that totals total cost of ownership of the initial capital expenditure within 60 months, typically. The problem with a lot of these solutions, especially if you're like doing a lot of block storage, iSCSI solutions, are that they are not particularly agile or elastic within the price range of a cloud operator, right? The redundancy is incredibly expensive, as is the support, and we all love NetApp and EMC. They spend $1 billion a year in R&D, but they aren't particularly good tools outside of the corporate enterprise. So as cloud operators, we've looked at other options to make our operating and capital costs more agreeable. So just to review a little bit more here, this is sort of what I'm talking about, right? You have an appliance with redundant controllers, redundant disk, multipath I/O, redundant power, unified management interface, and an array and volume manager, right? And you're usually dealing with hybrid pools, hybrid arrays. It's, by all measures, really interesting and good technology. But and this is what you would see in a typical deployment scenario, right? But it doesn't necessarily work well for a cloud operator, right? Think about, for example, who here has had to restore a RAID 6 array, a large RAID 6 array? Anyone? How long did it take? Right, exactly. That's been our experience as well. Restoring from outages, or not outages, but degraded arrays, it takes a long toll in terms of time and processing and I/O, right? When these things happen, and you're looking at, $20,000 to $50,000 as an entry cost to get into a reliable iSCSI block storage solution for the data center, it makes you scratch your head and go, is this really what we want? So for the past few years, as I'm sure most of you know, the software-defined everything model has really started to percolate, and you have fantastic stacks of software-defined networking, and so on and so forth. So we've been looking more and more at software-defined storage solutions, particularly GlusterFS and Ceph, who, not coincidentally, were both acquired by Red Hat within not such a distant time of one another, and have become the Red Hat flagship storage server. These are very overall Linux-friendly solutions. They have wide adoption. Today, I'm going to use Ceph as an example, but a lot of these concepts apply to both. So in terms of software-defined storage models, right, we're usually talking about off-the-shelf hardware, although Red Hat will give you a very specific list of servers they wish you to purchase, because I guess they're Red Hat. You're dealing with typically open source software, although there are some proprietary solutions in the software-defined storage category. Typically, there is no vendor equipment lock-in, no support commitment, and a great deal of elasticity, both in terms of deployment times and actual storage. We can go from 4 boxes of spinners to 100 within a day using technology like Ceph, for example, in a completely linear cost model, right? Basically, you're spending as much as the previous server's costs for a completely unified solution with unified hardware, no vendor lock-in, and performance that's going to scale in a linear fashion to the equipment you're installing, right? As you probably know from using RAID and striping disks that you have within an iSCSI model, the ability to scale your disk and array size and get certain performance boosts to a certain degree, right? One of the problems with the traditional scale-up model, right, is the fact that as you add disks, you realize really quick gains, and then you get the point where you start to reach I/O bottlenecks due to the fact that your solution is centralized within a very confined hardware platform. And you did scale linearly at the disk level, but you didn't add all those other things that you would have added in a distributed solution, like more RAM, more CPU, more controller bus, et cetera, et cetera. And so your solution may end up looking like this. And your costs do not necessarily increase linearly sometimes. Sometimes they increase at paces that may be more exponential. So in terms of the scale-up versus the scale-out model, I definitely think that it does definitely go hand in hand with the idea of software-defined networking, or at least it has in our experience. And given the different new challenges we have in density and scalability, it's definitely worth noting. The type of challenges a network operator or a cloud operator has compared to your traditional corporate network manager are really different, right? You may be tasked to spin up 20, 30 virtual machines if you're in the voice business and you turn up new call center customers. You may be asked to reserve multiple terabytes of call recording storage on demand, and it's a much more volatile and elastic type of engagement. And as an operator, you need a platform that's going to be allowing you to grow in that elastic fashion without really breaking the bank or sort of going deeper in the rabbit hole of vendor lock-in and commitment. The last thing that I think is really worth noting is that when you're increasing resources in the scale-out model, especially with Ceph like that, you're really increasing all of your resources. You're increasing your throughput because every server, assuming you have dual 10 gigabit NICs, so for every X number of disks, you're increasing your network throughput, you're increasing your controller throughput, CPU, RAM, and so on and so forth. It's undoubtedly a better bang for your buck. The other thing that I think is incredibly advantageous is the fact that you're able to use off-the-shelf equipment and that you're adding equipment in a much more non-disruptive platform. I mean, I've had some disasters upgrading NetApps, or have seen those, and I really appreciate the ease with which this occurs on more open source or open platforms. The low operational impact of new nodes has really been a blessing for us, and the overall performance increase. The risks are also there, of course. With Ceph, for example, you are treating each node as a complete failure domain. So if you are adding, if you have a small set of nodes, like 3, and storage nodes, and you add 2 more, you're basically putting 10% worth of failure domain in each node, and it certainly accounts for a risk. The other disadvantage of Ceph is that because it uses monitors, although it doesn't use a metadata server, which is really nice, loss of monitors will result in complete data loss. And while other platforms like Gluster will give you pretty easy access to your data in the event of monitor loss, this is not the case with Ceph. And it is certainly a risk that needs to be safeguarded. But as operators, part of our job is to monitor our equipment and monitor our data centers. So in most cases, this should not be a serious problem. The other thing that is a real scale-out risk is to make sure that deployment methodologies really fit the use. A lot of people really gung-ho with, for example, I/O throughput, and will add like OSD caching at the PCIe bus level without realizing that if they lose their journal cache, they lose the entire node, right? So while they were incredibly exciting about the IOPS they were getting, they weren't realizing that by creating a single point of failure at the caching layer with a single PCIe card, they were actually completely taking that node out of line. So in terms of overall summary, we believe that software-defined networking with a scale-out architecture definitely eliminates the scalability and performance bottlenecks that we've seen with more proprietary block storage solutions that are in the enterprise market today. It's a much simpler financial model, and it's simpler to plan for. And the fact that there's no proprietary lock-in or expensive maintenance upgrades makes the reusability of equipment and its redeployment much easier. So we're going to talk about Ceph a little bit. It was an open source project that was acquired by Red Hat, and it's a software distributed object store that has become very popular in the cloud computing space. It's widely deployed by OpenNebula, OpenStack, CloudStack, and Proxmox. And it has really three different sides to it. It was developed by SageWheel. They were acquired by Red Hat, I believe, in 2012. And since then, the project's only grown. As cloud operators, we're mostly interested in the block device properties of Ceph. But for those of you who may be using OpenStack, there is an object store. So if you are interested in S3 or Swift, there is that. And there's also a distributed file system. Our primary goal and purpose as operators is to achieve maximum density and virtualization. So we really focus on block devices. So this is another neat diagram, courtesy of Inktank. And here we have a graphical representation. The Ceph block device is really what we focus on. And what's really neat about the block device is that it distributes into little chunks across your server cluster. So if you have 5 servers doing what Ceph calls OSDs, which are essentially data objects, you're essentially striping all of your data across all those multiple nodes. Ceph allows you to replicate your data 2-fold or 3-fold, depending on how you wish to do it. And it also allows you to cache your writes in their journal, the OSD journal. And you can achieve incredible speeds, especially with the use of SSDs over spinners or PCIe SSDs. There are people out there doing a tremendous number of IOPS in the multiple gigabytes per second for all kinds of scientific applications. Our requirements aren't as hardcore because we're doing virtualization, but it's a pretty amazing platform to behold. As far as the way it's laid out modularly, RADOS is the low-level framework. And RADOS stands for Reliable Autonomic Distributed Object Store. And what it does is it manages all the self-healing, managing, and intelligent nodes of the storage cluster. What that means is that from a physical view here, every disk has a file system, and then an OSD on top of it, which is an abstract object layer. And what that OSD actually does is it serves objects to file system clients. Now, to put this in context of what we're doing, right? Our file system clients are actually accessing Ceph as block device clients, right? So when you're, for example, running iSCSI, right, and you're mounting an iSCSI target on your VMware or KVM or whatever it may be, you're mounting a block device. Well, what Ceph allows you to do is to do essentially the same thing, but in a much more distributed way. So you're actually hitting a monitor, and then somewhat magically, your request is querying data across multiple servers. So in terms of the results of that, you get a much more distributed experience, which is highly reliable, but can also be much faster. So the primary libraries are librados, and that's what your application would actually access. And LibRADOS is socket-based, extremely fast. The RADOS gateway is an application that speaks REST to the world and then uses LibRADOS to speak to the cluster. That gives you a tremendous amount of flexibility in terms of building storage applications in a RESTful manner. We, like I said before, are more interested in the block device, and the block device is called the RADOS block device. Usually called RBD. And this is what allows us to decouple virtual machines from hosts and allows us to, like I said, stripe multiple images across multiple hosts. You have, of course, like, copy on write, which is really important. Snapshotting, right? One of the things that you probably used to is, QCOW files. If you're running KVM, that's great if you're mounting them on an already pre-existing file system, but because this is a block device, you would need some way to snapshot your images and do copy on write clones and things like that. So as far as cloning, snapshotting, and thin provisioning, this is really a phenomenal platform for doing that sort of thing. Hypervisor access comes from the librBD, and so you get here you have one VM. In real life, you would have a lot of virtual machines across a lot of hypervisors accessing the cluster. But again, what you're doing here is all of those virtual machines are mounted as block devices, as native block devices. And if you had actual machines that were bare metal, you could also mount them as block devices through librBD as well. They would just mount under dev, and the operating system would see them as a disk. The advantage, again, is you're striping that image across multiple servers, much higher reliability, much higher speed, no vendor proprietary lock-in. The way this happens is through an algorithm called the crush map that basically creates placement groups that locate, fetch, and allocate data. So when you have an outage or a downstate in a node, it reallocates that map and fetches information and performs writes. This is a big departure from your typical distributed file system that uses metadata and allows a lot greater speed, essentially. So to put this in context of a data center deployment, right? You would have your hypervisor cluster on the left. If you're using OpenStack, the framework you would be using is Cinder for block storage access. OpenNebula has their own Ceph module. Proxmox has a Ceph plugin. And these are all basically facilities within that framework to facilitate block storage operations, right? Everything from cloning, snapshotting, thin provisioning, et cetera, et cetera. That, of course, allows for much greater efficiency, right? When you're doing copy and write and thin provisioning, you're not really creating a new image until you write to it, thereby being able to create tens or hundreds of thousands of images at almost native speeds. So what you see in the center here are your Ceph mons, right? Your Ceph mons are the actual file system monitors that keep the crush map active. You see 3. 3 is a very common number in clustering, right? Due to quorum issues. And then on the right, you have your OSD nodes. These are the nodes that carry the actual data that is being shuffled around by the monitors. So in terms of applications for Asterisk, well, really the sky's the limit. But for us, the real application for Asterisk is our role as an infrastructure provider, and the fact that we don't necessarily have the time to restore from backup the old way, provision the old way, as far as availability, this gives an operator unprecedented availability without the prior constraints of the more traditional two-server replicated data block device, like replicated EMC or NetApp. In terms of best deployment practices, they start, in my opinion, at the switch layer. I'm sure that if you've deployed iSCSI, you will see this time and time again. Jumbo frames and cut-through switching could, boost your throughput, I/O throughput, depending on what it is you're doing, whether reading sequentially or not, by 50, 60%. 10 gigabit switching, in my opinion, is a must, as well as network segmentation. In terms of actual Ceph is concerned, there are probably too many best deployment practices to name, but a few that we have seen are replica counts. Depending on what your business is and what your purpose is, you may want to choose to do 3 replicas instead of 2. You'll pay, obviously, a performance penalty, both locally, the controller, and the network level. The other thing that I would say is that SSDs dramatically improve performance, even as enterprise SSDs, not even PCIe SSDs, for the journal cache. XFS, in my opinion, is probably the best choice right now. Ceph supports ButterFS, but I don't think anyone is really running ButterFS in production. We'll post these settings on the Asterisk site if anyone wants to see them. But we definitely do file store flusher, and make sure to watch the object replication. The things to be aware of, in our experience, are actually Ceph itself. The biggest single point of failure in a Ceph deployment is Ceph. And that's been said by a lot of people, and it's true. If you are not diligent in maintaining it, you will find that the application will fail, especially in terms of upgrades. If you run out of monitors, you will not be able to access your data. If you do not distribute your OSD journal, you will lose, for every journal you will lose all the disks on that server. And finally, latency, as you know from other networking storage projects, is the killer of I/O, and that applies very much to Ceph. But other than that, it's a very cool platform, and you guys should check it out. Any comments, questions, criticisms? We're migrating to it. We're very, very cautious, and it's also more expensive than Gluster. So there's a certain amount of comfort level, but our new rollout at our new data center is going to be all Ceph. Yeah. Yeah, so we have a lab with a rack full of pizza boxes, and we've been trying to break it for about 6 months, since April, and we haven't really achieved much success. So I mean, obviously you lose all your monitors, your toast, right?
All right, we're gonna have to.
I can't hear you, I'm sorry.
Have you done any testing and validation with commercial SDF platforms?
No. No, I haven't.
We're going to have to call it there. Thank you very much.